Hi everyone, welcome to our third video for week 3 about finding probability with the normal distribution. So our last video, we introduced the normal distribution. Now we're going to learn how to use it to find probability for events in the real world. There's 3 methods to do this. The first is using that standard normal distribution and z-scores that we talked about in the last video, and then reading the probability from a table. To do this, the very first thing you're going to have to do is convert any given x values into z-scores using the z-score formula. The next thing you'll need to do is draw a labeled standard normal curve and then shade in the area or probability of interest. What section of that curve are we looking at? Where are the range of values that I'm interested in? For a probability that z is less than a given value, you're just going to read that from the table. So the table is set up for z is less than a value probabilities. If you have the opposite, z is greater than, you're going to do 1 minus the value from the table. If you have 2 values, z is between a and b, you're going to look up the value for b, look up the value for a, and then subtract them, bigger minus smaller. So again, if you're using a standard normal table, those tables only find the area to the left, and that's why B and C up above look a little funky, because we're finding something that's not exclusively area to the left. So we're having to kind of work with the value in the table to get what we're interested in, using the complement rule or using a little bit about what we know about geometry. So here's a picture that I'm looking for when I talk about draw a labeled standard normal curve. You'll notice 0 is in the middle. Those lines should be 1, 2, and if there's a third one, 3. So 1 standard deviation away, 2 standard deviations away. And then I've labeled that variable x that I was interested in that I've converted to a z-score. So this is that z-score of interest. And I've shaded the area that I'm interested in. And this picture goes with A. This is what's the probability z is less than A. You'll notice that the area shaded in green, I shaded in the same direction that that inequality pointed. And that's going to be a common theme. If the inequality points to the left, shade to the left. If the inequality points to the right, shade to the right. If z is between 2 values, shade in between those 2 numbers. So here's a picture of what that standard normal distribution looks like. So give me a second to get my annotate up, and let's take a look at how to read this table. So let's say that I'm interested in finding the probability that z is less than 2. Ooh, sorry, that was messy. Negative 2.31. And you'll notice 2 places past the decimal. We talked about that. This table is why we write z-scores to 2 places past the decimal. In our table, we look for the first digit in front of the decimal and the 10th place. So the 1's place and the 10th place. And that's what we're looking for in the column this way. And then the very last digit, the one in the hundredths place, is what we look for along the top. So for ours, we need to find negative 2.3, which is right here. And then we need to find 0.1, which is right here, and figure out where they intersect, which is right here. So the probability that a randomly selected z-score would be less than negative 2.31 is about 1%, 0.0104. One thing you'll notice about this table is that those probabilities are carried out to 4 places past the decimal. And that's some of why you saw me rounding probabilities last week to 4 places. A lot of things that we do in stats are tied to what these tables look like, because when I took stats back in the 90s, we didn't have calculators with statistics functions, and we didn't have GeoGebra. And so we relied exclusively on these data tables to do these problems. Okay, my assumption is very few of you are going to do this just because it's time consuming and we live in 2023. So let's take a look at our other 2 methods. The second method is the TI-84s. TI-83s also do this, as well as the TI-Inspires. Directions for TI-83s are the same, except that it won't give you prompts for this. You need to know that you enter the data in this order without being told. And the TI-Inspire, it's the similar function call. It's a normal CDF, but it's in a different menu, and you get to it a different way. So for 84s, you're going to press second and vars to open the distribution menu. So let me get my calculator on the screen here. So hopefully everybody can see my calculator. If I press second and then vars, there's 2 options, DISTR for distribution and draw. And you'll notice it says select 2 normal CDF, cumulative distribution function. There is a PDF in most calculators. We do not want it. We want option 2, normal CDF. And it's going to ask us for 4 pieces of information: the lower boundary, the upper boundary, so the 2 edges of that shaded area, the mean, and the standard deviation. And you'll notice a few things on my calculator. It says the lower is -1 E99. That's a -1 with 99 zeros after it. That's a really, 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 really small negative number. And what that's telling us is that that's approximating negative infinity, because those bell-shaped curves just keep going forever and ever without ever touching the axis. So we're using the biggest negative we can to approximate that curve going out to infinity. It hasn't given us an upper, because what it's prompting us to do is give it a z-score or an x value. And it's assumed we're going to give it a z-score because it defaults to 0 and 1. You don't have to do this. You can put any value in here you want. So lower bound of your shaded area, upper bound of your shaded area, your mean, and your standard deviation. If it's a less than problem, you're going to have to use that -1 E99 that kind of defaults in the calculator. If it's a greater than question, you're going to need to use 1 E99 as your upper boundary. And if it's between 2 values, you just use those 2 values. Really quick, just to show you how to pull that up. If I wanted to type an upper boundary of 1 E99, I type 1. And then to pull that scientific exponent notation, I'm going to hit second, comma. And you'll notice there's a little EE in blue above the comma button. That's what we're accessing. That's how the calculator does scientific notation. 1 times 10 to the 99. This is the whole curve from negative infinity to positive infinity. If I run this on my calculator, I should get 1. which is good. That means the calculator is doing that correctly. We've accounted for everything. We get 1 as our answer. GeoGebra is a little weird in that it will only do areas to the left, kind of like the table. But it will do calculations for any mean and standard deviation. You don't have to convert to z-scores first. The command in GeoGebra is normal, and then it asks for 3 pieces of information: the mean, the standard deviation, and the upper bound. So if you're doing px is less than a, you'll do normal, whatever the mean is, whatever your standard deviation is, and then that upper bound. If you want x is greater than a, you have to use the complement trick, 1 minus, and then the normal function. If you've got x between 2 values, you have to do those normal function calls separately and then subtract them. Bigger one first, smaller one second. So 2 and 3 here are very similar to the modifications we have to make for using table E. Okay, so we're going to do some examples so that you can see how this looks. And I'll try and do it both with the TI-84 and GeoGebra so you can see how it looks on both. So this one says the final exam scores in a statistics class were normally distributed with a mean of 63 and a standard deviation of 5. Find the probability that a randomly selected student scored more than 65 on the exam. Find the probability that a randomly selected student scored less than 85. And find the 90th percentile. That is, find the score K that has 90% of the scores below K and 10% above. So let's start with part A. Find the probability that a randomly selected student scored more than 65 on the exam. So let's pull my annotation up here, get that out of the way. So first thing I'm going to do, I'm going to pick through that problem. And I can see that my mean is 63. And I can see that my standard deviation sigma is 5. And I can tell that they say find the probability, so I'm looking for a P, that a randomly selected student, X, is more than 65. So Px is greater than 65. What is the likelihood that I randomly select a student that got a 65 or higher on the test? So let's do that on GeoGebra, or sorry, TI-84 first and then GeoGebra, since I've got the TI-84 up here. So I've got my calculator on the screen, hopefully. And we're going to go second vars. We're going to choose option 2. And then we're going to enter some numbers. And I'm going to draw a picture of what I'm calculating before I enter my numbers. So here is a number line with all those test scores on it. I know I'm normally distributed, so here's my normal distribution. I know the mean is right in the middle, so that should be 63. And then I know my standard deviations go in either direction, and that I'm counting by 5. So my standard deviation is 5. So this is going to be 68. 68 plus 5 is going to be 73. We go in the other direction, I'm going to end up at 58 and then 53. I'm going to grab a different color here. I'm interested in greater than 65. So 65 is just a little bit past where our mean is. And we want greater than, so I'm going to shade to the right. So I'm interested in this area here. And looking at that picture, my lower bound is that 65. My upper bound is the edge of the graph. It keeps going forever and ever and ever. And I know if I've got a more than problem where my graph keeps going to the right forever, I should use 1E99 as my upper bound. You'll notice the calculator remembers what I did last time. So I already have my upper bound in there correctly, but I do need to fix that lower bound. So my lower is 65, my upper is 1E99, my mean is 63, and my standard deviation is 5. And we're going to go down to paste and enter, and it just sticks that normal CDF command on our screen. And then we hit enter. And our calculator is saying that this probability is 0.344, and then we've got 5, 7. I'm going to round that up to 6.3446. Let's double check. Let me pull up a, sorry, I just had a total brain fart. Let me pull up a GeoGebra screen so we can see what that looks like. So we know for GeoGebra, when it's a larger than, we want to do the complement trick because GeoGebra will only find areas to the left. So we're going to do 1 minus, and then the function call is normal. And then it wants the mean, the standard deviation, and that boundary point of 65. And you'll notice it's giving us that exact same number that we got on our TI-84. It's giving us 0.34457 something, something, something. So 0.3446. If you've got a table handy, I'd encourage you to check that, convert that mean, or not that mean, that X value to a Z-score, and check that you also find this in the data table. You would again have to use that complement trick. Okay, let's try another one. So this one is the probability that a randomly selected student scored less than 85. So we'll start the same way. Our mean is still 63. Our standard deviation is still 5. And we're interested in the probability that a random student X scored less than 85. So normal curve. Mean is in the middle. And we count by 5s. We're interested in 85. So that's way out in that tail. That's going to be way out here somewhere because this is 73, 78, 83, 85 is going to be like out here somewhere. And we're interested in getting less than 85. Less than is this way. And looking at that picture, I'm way out in that tail. I'm way past 2 standard deviations. I'm actually even past 3, which would be 78, and 4, which would be 83. I'm out past 4 standard deviations. That means this is almost the entire curve. So before I even pull up my TI-84, I have an idea that my answer is going to be pretty darn close to 1. But let's check that. So we're going to pull up our calculator, second vars, normal CDF. In this case, our lower is the left edge of the graph. So that's the -1 E99. The upper is now 85. And our mean is still 63. Standard deviation is still 5. And yeah, we get something that almost rounds to 1. When you see this, do not round it to 1. I know that when you see really small numbers or really big numbers, it is tempting. But it is statistically important that this is almost 1, but not quite 1. So 9, 9, 9, 9. I count 5 nines and then a 4, 5. And you don't have to go out that far. You could cut it off here and round it up to 9999995. But this tells us that it's almost guaranteed. I expect that if I randomly select a student, almost every single student I selected had a score less than 85. But it's not completely impossible that they had bigger than 85. It's just very unlikely. And that's the difference between having a really long 0.9999 and a 1. 1 means it happens every time. That 0.999 means there's a little wiggle room that it doesn't always happen. There's another option there. Okay, let's do the next one. This one says find the 90th percentile. That is, find the score K that has 90% of the scores below K and 10% of the scores above K. So I'm going to start the same way. I'm going to label my stuff. 63, sigma is 5. You wouldn't have to do this because you already have it on your homework. And then we know we want the X value that gives us the 90th percentile. So I'm going to draw a picture of what they're telling me before I start trying to figure out what I'm finding. So here's our normal curve. And they say we're looking for a score K that has 90% of the scores below K and 10% of the scores above K. So let's label this. We know that this is 63, 68, 73, 78, and then in the other direction, 58, 53, 48. And our mean is right here in the middle where the peak is. That's our mean. So I know that the mean cuts that graph in half. So I already know the area to the left of the mean is 50%. And I know that because there's 68% between 58 and 68, half of that's up here. Half of 68 is 34. So 50 plus 34 is at 84. So I expect my 90s probably here, somewhere between the first and second standard deviation on the right. I expect that that's where K is sitting. And what they told me is that this area here is 90%, 0.90. This looks exactly like the opposite of what we just did. We knew where our upper shaded boundary was. It was at 85. We didn't know what the area under the curve is. Now we have the opposite. We have the area under the curve. I need the K value that forms that upper boundary. To do this, to go backwards, to undo that normal CDF, we're going to use something called inverse norm or inverse normal. So if you're on a TI, it's going to be called inverse norm. If you're on GeoGebra, I think it's called inverse normal. They spell it out. And we'll take a look at both. So let's pull up our handy dandy TI, clear this, and we're going to go to that same menu, second vars. And you'll notice right under normal CDF is inverse norm. And it asks for three things: the area to the left, and then the mean and standard deviation. So we know the area to the left is 90%, 0.9. Our mean is 63, our standard deviation is 5. So if we hit enter, that gives us 69.41 if we round. So let's jot that down. So TI is saying K is 69.41. And if you look at where my boundary is sitting in my picture, I have it just a little bit bigger than 68 using the empirical rule. So that makes sense in terms of how I drew my picture. That K value makes sense. Let's try it on GeoGebra so you can see what that looks like in the other calculator. And actually, let me make this a little bit bigger if I can, maybe. There we go, so we can read it. So I'm going to start typing inverse normal, and you'll know it. Notice it pops up. And what it's asking for is the mean, the standard deviation, the area to the left. So it wants the same thing that the TI does. It just wants it in the reverse order. It wants the mean and the standard deviation first, and then that area to the left. And again, just like our TI-84, it's giving us 69.41. So in this problem, we get two tools. We get the normal CDF tool that we know, but we also learn about inverse norm, which is how we undo the normal calculation. So inverse norm or inverse normal will take you from a probability or area to a boundary value. Okay, what I'd like you to do is pause the video really quick and do this problem on a calculator, and then we'll go ahead and go over the answer together. Okay, so try it 6.9 says the golf scores for a school team were normally distributed with a mean of 68 and a standard deviation of 3. Find the probability that a golfer scored between 66 and 77. So I am going to do exactly what I did in the last few. Write down the information I was given, draw my picture, use my calculator. So normally distributed, mean of 68, and a standard deviation of 3. And it says find the probability that a golfer scored between 66 and 77. So 66 less than X less than 77. So let's go ahead. That's a messy line. Try that again. Draw our normal curve. We know our mean is in the middle, and that is 68. And then we know we're counting by threes. So 71, 74, 77, 65, 62, 59. Please double check me. I'm pretty sure I added and subtracted by 3, but it's been a long day. And they're asking us between 66 and 77. So 66 is right about here, a little bit bigger than 65. And then 77 is right here, it's 3 standard deviations above the mean. So I'm going to shade in the area between those two boundaries. And looking at that, that looks like that's more than half the curve. I know if I started at 68 and went out to 77, that's almost half. So I'm probably at just a little bit above half of that curve. So I'm expecting a number at about or slightly bigger than 0.5. But we're going to check. So this time I'm going to do it on both, just so you can see, starting with the 84. Second bar is normal CDF. In this case, our lower is 66, our upper 77, our mean is 68, and our standard deviation is 3. And we get something clearly bigger than 0.5, so that's good. And we're going to write that down, 0.746, and then 1.5 rounds up to 2. And then let's go ahead and do the same thing on GeoGebra. So we know for GeoGebra, we need to enter the bigger normal function call first, and then the smaller. So I'm going to do 77 before I do 66. And GeoGebra wants the mean and standard deviation first. GeoGebra does it backwards from the TI-84. So a mean of 68, a standard deviation of 3, an upper bound of 77. And then I want to subtract from that normal, and then same mean and standard deviation, 6 and 3, and then a lower bound of 66. And we get, just like we did on the TI, 0.7462. What I'd like to do is show you something kind of cool on GeoGebra that the TI can't do. So here, when you go up to the top next to GeoGebra, there's a little toggle menu. And GeoGebra can do lots of different things, but you'll notice that bottom says probability. And when you click on it, it has several distributions listed in it, including binomial, which we talked about, but it defaults to the normal. And then it asks you for information. So we just did a problem where our mean was 68 and our standard deviation was 3. And we want an area between two numbers, specifically between 66 and 77. And what you see is that in the probability calculator, GeoGebra draws that picture for you, but it also calculates it at the same time, 0.7462. So you can use the probability toggle instead of doing it with the graphing calculator, which is what we did the first time. So if you're on GeoGebra, the graphing calculator does just fine, but you can also use that probability function. And again, lots of probability functions. We're going to use normal, student, chi-squared, and F distribution. And we've already seen binomial, and you'll notice it does binomial as well. Okay, there's another try it. I'm going to post the answers really quick, but I'm going to give you just a second to try it on your own, and then we'll come back together to look at the answers. Okay, so let's start with part A. We've got 2,000 students who took an exam. Scores on the exam have an approximate normal distribution with a mean of 81 and a standard deviation of 15. Calculate the first and third quartile scores for this exam. So let's go ahead and go through this problem. I'm going to do this a little bit quicker since we've seen a few. We know the mean's 81. Standard deviation's 15, and they ask for the first and third quartile scores. They're asking for scores, meaning they're looking for X values. And I know that the first quartile represents the lowest 25% of the data, separates the lowest 25 from the upper 75. And the third quartile separates the lower 75% from the upper 25. So they're giving me percentages or probabilities or areas under the curve, and they're asking for those X values. So let's go ahead and draw those pictures really quick. So normal distribution. We know our mean is in the middle, so that should be 81. And then we want the lower 25 and the lower 75. So I'm going to do the first one in green. That's probably somewhere down here. I'm just guesstimating. So that's my Q1. And then my Q2 is probably going to mirror that, or not my Q2, sorry, my Q3 is probably going to mirror that up here. And all of that. What this means is we're going to need to do 2 inverse normal calculations, one for Q1 and the 25%, one for Q3 and the 75%. So for Q1, I'm going to do inverse norm. I've got a percentage of 0.25 with a mean of 81 and a standard deviation of 15. If you're on GeoGebra, remember it's going to reverse those. It's going to want the 81 and 15 first. And then for Q3, it's going to look almost identical. Inverse norm, and then 0.75, 81, 15. But let's go ahead and pull up GeoGebra and do that. Not GeoGebra, sorry, the TI-84 and do that really quick. I'm going to erase some of this just so we can see what we're doing here. Okay, that looks a little better. So we know we want inverse norms, second bars, down to option 3. Area is 0.25, mean of 81, standard deviation of 15. So I know my first quartile is at 70.88. To do the next one, I'm actually going to do a cheap trick here. I don't want to have to go back to second bars. I'm going to hit second enter, and it pulls up the last thing I typed, which is my last inverse norm function call. And all I need to do is change that 25 to a 75, and then hit enter again. And it gives us Q3, which is 91.12. 70.88 rounds about to 71. 91.1 rounds down to about 91. So the first quartile is about 10 points below the mean, and the third quartile is about 10 points above the mean. Okay, second one says middle 50% of exam scores are between what 2 values? Again, notice they're asking for values. So similar idea to the last one. We're going to draw a picture and try and sort out what they're asking. So we know our mean of 81 is in the middle, and I want to block off the middle 50%. So let me start drawing these hash marks. 1, 2, 3, 1, 2, 3. We know that according to the empirical rule, that the middle 68% is between 1 standard deviation below and 1 standard deviation above. 50% should be inside of that first standard deviation. So we know that this is 50% here in the middle. Well, we also know something else. If I have 50% in the middle, that leaves me 50% for the outside. And what's half of 50%? 25. So I know that this chunk over here is 25%. I know that this chunk over here is 25%. And that means that this chunk here, from this edge that way, is 75%. What that means is that upper bound to the middle 50% is just our third quartile. And that lower bound is just our first quartile. Let's check that, but that should work out, yeah? We just did that same thing before. We go back on our calculator, second bars, inverse norm. There's our 0.25, same mean, same standard deviation. So we already know what these values are, 70.88 and 91.12. So that one was a little tricky. This one was indirectly asking you about the same thing part A did. Okay, so hopefully you've had a reasonable introduction to how to find probabilities or areas under the normal curve using your calculator or GeoGebra. There's going to be a couple more videos on how to do this, as well as some general word problem strategies coming. If you have any questions, let me know. Otherwise, I'll have office hours on Tuesday and Thursday between 12 and 1 and 7 and 8.